Right, good afternoon everyone, to the people here and the people online. Thanks very much for being present for this, for our talk on this Monday afternoon. Dr. Peter Jenniskens has been at the Planetary Space Events Conference in Stellenbosch and very kindly agreed on his way back to stop off and give us a talk on some of the work that he's been doing, was doing currently. Peter is a graduate of Leiden University, where he did his degrees, including a PhD in interstellar matter that he completed in 1992, before going on to NASA Ames in California to do a postdoc, and they've never let him go since then. So he is still there, working at the SETI Institute in California, where his main interest is on astronomy, with a specific emphasis on meteors and fireballs coming into its atmosphere. He's the author of more than 200 publications on this and various other subjects, as well as 2 books. His second book has been released this year and is apparently an award-winning book. He bills it as a birder's guide to meteor showers, so a popular book that has received recognition. And he's very motivated and committed to the study of meteorite falls, satellite re-entries and space debris re-entries, and the need to work with the public on observations and collecting information on that. So, Peter, thanks very much for coming up to talk to us, and we look forward to the talk, which the title of, From Where in the Asteroid Belt Do Different Meteorite Types Originate?
Thank you. So very happy to be here at Wits. Last time I visited was back in 2018 when we had a meteorite fall in Botswana, in Central Caribbean Reserve. And interestingly enough, you guys had a meteorite fall last year, which is the same meteorite type. So we've had 2 of they fall in a group called HEDs. Howardite Diogenes. So we have 2 of these falls now here in South Africa in a short period of time. So this one is I'm talking about today is a really exciting project. Last year I've been looking into this question: where do our meteorites come from in the asteroid belt? And I think there is sort of a change in thinking about that. We used to think that our meteorites were an erosion product of all the various collisions happening in the asteroid belt, that you would sort of get random meteorites from everywhere. But I think we're starting to realize now that we are getting our meteorites from the most dramatic, the most massive, the most impactful collisions that happened in the asteroid belt in the past 100 years. Those collisions were so strong, so big, that they produced debris fields of asteroids a kilometer in size that we can recognize in asteroid surveys. So we're literally seeing the clusters of collisions of debris within the Haliana families, within those larger families asteroid debris field. And that I will show you in this talk. So in my overview slide here, I'll show you what the thing is. On the left, you see a sort of a cross-section of the asteroid belt. So what is shown here is semi-major axis, which is basically going from just outside the orbit of Mars to sort of halfway up the orbit of Jupiter. The more you go out, the longer it takes for something to go around the Sun. So with the semi-major axis increasing, you're also increasing the orbital period. The 2 are related. And at certain orbital periods, you see there are gaps, like 2.5 AU, there's a gap that's called resonance. And that's because meteorites are going around asteroids are going around the Sun 3 times when Jupiter goes around once. So you have these ratios with the orbital period of Jupiter across these vertical lines. The resonances are very important for my story. And then going vertical is the inclination of the orbit. So how steep are the asteroid orbits tilted to the plane of the planets? The further you go up north, sometimes I'm saying the sign of the inclination, sometimes the inclination. It's pretty much the same because we're talking about inclinations between 0 and 20 or 30 degrees. So we're talking that everything is sort of in a flat disk. Now, every point in that diagram is a very old diagram back from 2000. This is from the slow nuclear sky survey cards. Every point is one asteroid that was for which a color was determined. And the colors of the asteroids are given here as orange for asteroids that are stony, and blue for asteroids that are primitive, that are carbonaceous. And then there is this sort of purple group you see there in the top right corner. That's the EOS family, and they're sort of in between. They are thought to be these CO, CV, and CK type carbonaceous chondrites. So these are primitive asteroids, but they don't have a lot of carbon in them. They almost look more like ordinary chondrites. So those are that group. And then there's this big group of green colored asteroids there, and those are the asteroids coming from asteroid Vesta. Those are basaltic asteroids, and they really stand out from everything else. There's no other debris field in asteroid belt that has those. And for a very long time we suspected that our HEBs, like the one that fell here in South Africa last year, and the one that fell in Botswana back in 2018, that those coming from that area. And the trick is to see if we can assign some meteorite types to all those other debris fields. As you can see, there's a lot of debris fields that are sort of orangey color. So there's a lot of stony ones, and there's also a lot of them that are blue in color, a lot of primitive ones. So which meteorite type corresponds to which of these asteroid families? Now, you have to sort of know how this works to sort of follow my story. So you have a collision happen in the asteroid belt. A lot of debris is created. That debris, some of that is relatively small, like 2 meters in size. Some of it is really big. Once that debris is seeing the sun, it absorbs light at noon, gets hot, the asteroid rotates, and it will radiate that light, that energy, in the infrared at the hottest time of the day, say at 3 o'clock. So if you're rotating this way, then you're radiating your energy there, and that means that you get a kick force moving in that way. If you're rotating the other way, then you're emitting your energy there and you get kicked backwards. So what this effect does, it's called the Yarkovsky effect. What it does is it changes the orbital period of the orbit. So you start up with a collision somewhere in the debris field. So look, for example, at this debris field to see how spread out it is in C major axis in orbital period.
I'm very sorry to interrupt you.
Yeah.
I'm confused by what you mean by debris field.
So all of these groups, all of these clusters, are called here young families. They are the product of collisions in the asteroid belt. And a lot of all these big ones that you see are collisions that happened a very long time ago. Within these debris fields, there are more recent collisions, they're clusters. And so that's what I mean with the debris field.
But it's not the debris field of meteorites that you see on the Earth.
No, exactly.
That's a different use of the same word.
Yes.
Okay.
Yes. Some asteroids are just looking at different scales. So for me, a debris field I can sort of imagine something by, as in a massive amount of fragments scattered all over the place. That's what that is. The thing I wanted to point out here is that many of these debris fields are spread out in C major axis, and that's because of this Yarkovsky drift. That asteroids move one way or asteroids move the other way over time. And when we have a collision that creates our meteorites, we see the same thing. So we have a collision, we have this meter-sized asteroid created, which is part of the brief field. This meter-sized asteroid is now going to move this way or that way, depending on which direction it's spinning. And for a meter-sized object, that motion is pretty quick. So it takes only about, let's say, 1 million years for the rock to move from the collision to the resonance. So that's number one. The rocks spread out. Small ones pretty quickly, they go pretty quickly to the resonance. Big ones take a long time to move to the resonance, they're hard to move. So that's the first step in evolution. Once they hit the resonance, very quickly, they go from more or less a circular orbit around the sun in the asteroid belt to a much more eccentric orbit, much more elongated orbit. The point closest to the sun comes in, the point furthest from the sun goes out. The orbital period stays the same, it stays in resonance. So the perihelion comes in, the aphelion goes out. If it goes out too far, you're hitting Jupiter, or Jupiter's orbit. That's bad. Jupiter is such a big mass that it can easily scatter your stuff. So it is, come in, this way and somewhere. Just let me know when the students have arrived.
No. They'll come in groups of friends.
Some of them. Otherwise, I have to explain this story again.
We'll explain it to them.
It's important.
And you see this story. Sort of pan out through the rest of my talk, because this is really why we get the meteorites.
So when you said kilometer-sized objects, are you talking about the impact of 2 kilometer-sized objects in the asteroid belt creates the scatter?
No. So typically, something big is destroyed by something small. It's the target is usually a lot bigger than the projectile is. Often the target is just damaged, a cratering event, for example. You throw a bunch of stuff off. But most of the debris you see is from the target object. And that's the reason why all these things have the same color. The projectile itself, because it's so much smaller, is basically not adding to the family. So these debris fields stand out by just having getting more of them. You see a lot of asteroids in that spot, but also by them having the same color, a color that's sort of representative of whatever the target asteroid is. But that's not what causes the spreading. When you have a collision, you're basically having an ejection velocity. You eject stuff away, but it's relatively small velocity, so it moves as a group and it continues to move as a group around the sun. The spreading, increasing the orbital period or decreasing the orbital period, that comes from this Tsiolkovsky effect. Basically, the sun's radiating, you're absorbing the light at noon, and then you emit the light at the heart of the day in the afternoon. You increase the orbital period, or if you spin the other way, you eject it in the morning, and that way you decrease it. And that basically has all this, or you say you start here, that has you move this way, or has you move that way. And so all this wheel spreading out like this, most of that is from the Tsiolkovsky drift. So then you get into the resonance. Now what a resonance does is a resonance basically means that you go around 3 times as an asteroid around the sun, while Jupiter goes around 1 time. If that ratio is exactly the 3-to-1 ratio, then you start not seeing Jupiter randomly in the sky anymore. Every time when you are closest to Jupiter's orbit, Jupiter is either there, or there, or there. And that means that now you're going to feel an effective force from Jupiter. And that's why an orbit is very rapidly changing from sort of going around as a circle to becoming very elongated. And the way it gets elongated is the beginning point, closest point to the sun comes in, and the point furthest to the sun goes out. Once you're in that sort of eccentric orbit, then you start having collisions with the Earth or with Venus. And any, not just collisions, any sort of close encounter with these planets can change your orbital period. And that means that now you're putting your asteroid out of the resonance. It's no longer in the resonance, but now it sits in this very eccentric orbit, which we call a near-Earth asteroid orbit. And it's doing that for a very long time, because Earth is a tiny, tiny target. It's really hard to hit. And so basically you have this collision in the asteroid belt, the cost you within a million year brings zone to the resonance. The resonance sends it immediately into an Earth-causing orbit, and then it sits there. And it evolves. It will have more close encounters with the Earth. And what that does is it makes the orbit shorter over time. And it also, you can have close encounters that increase the inclination. But then you have to just wait for it to hit us.
So, are you saying that most of our meteorites come from those resonance places?
Yes, and that's I'll show you. So these are your typical orbits on which meteorites are seen to hit the Earth. This was a picture I drew back in 2018 when we had a bunch of 2 cm type Carbonaceous chondrites observed, and we had a bunch of LLs and a bunch of Ls, ordinary chondrites observed. And already, if you look at it with a squeezed eye, you can see there are some differences between the two, in the sense that the CMs seem to be wider; they go all the way almost to the orbit of Jupiter, while the green ones are fairly short orbits. So there seems to already be a sort of an indication that the meteorites on different types come to us on different orbits. And that is now confirmed. We can really see patterns in that. So single major axis is this thing. It's basically half the orbit. So it's half of the major axis of the orbit, but it's basically a function of the orbital period. So that's what single major axis is. Inclination is basically how steep are the orbits tilted on the plane of the planets. And if you look at those two things, and you look at all the asteroids, all the meteorites coming to the Earth, then it sort of looks like this. Plotted is single major axis on the bottom, inclination vertically. And then you basically look at the 20 centimeter size meteoroids, and you see how they evolve, how they change their orbits after 50 million years. And then you look at those orbits that come close to Earth's orbit. And that basically gives these diagrams. So if your source is at 1 degree inclination, so really almost in the plane of the planets, and the source is the collision was in the inner main belt, then you see that most of the meteorites are coming to us with C major axis of 2 AU. That's that resonance. It's actually the resonance that sits at the inner part of the asteroid, it's called the U6 resonance. And but you can see that you still expect most of your meteorites to have that resonance value. And then there is a sort of constant inclination goes in, and there is from the C major axis getting lower and lower from close encounters. And then you see also that the inclination spreads out, so you get cases that have much higher inclination. If the source sits at 10 degrees, like in this case, you see that again you're expecting it to come in from the U6 resonance, but now your inclination sits at about 10 degrees. And the same for if your source is in the middle belt, then it's the 2 to 3 resonance, it's this resonance, the 3 to 1 resonance, this resonance of 2.5 AU, that gives you most of the meteorites. So if the source is at 1 degree, and the meteorites mostly come still with the C major axis here, and then sort of have this inclination distribution coming in. And if they are sitting at 10 degrees, again this situation. In this case, the 3 to 1 resonance itself can also increase the inclination. So the C major axis is the energy of the orbit. It's the orbital period. And it's hard to change. You have to literally do the thing with the Yarkovsky, where you add the sun's energy to the object, or you have to have close encounters with the planets to change the CMH axis. The inclination is also hard to change. Again, you need to either have a resonance pump it up, or you have a close encounter with the planets to have it. So when we, Tim and I, look at these meteorite falls and look at the orbit of a meteorite fall, what we're looking for, what was the inclination of the orbit? And what was the CMH axis of the orbit? Inclination is usually easy to do, no problems. The CMH axis is hard because you need to get the initial entry speed correctly. Yeah. But that's the two types of data that we're looking for. So this is basically the theory. Now we have some other tools that we can use. One is let me first tell you about that type of observation. So the best orbit of an impactor you're going to get if you actually have an impacting asteroid, as in the asteroid is seen in space, in track for a period of time, predicted to impact, and it's then actually impacting us, and you can find a piece of it. And that has only happened a few times. And one of those times was in Motopipan, Botswana. And so I've gone out to all the cases where we had this happen and helped the local research teams find the meteorites. So we have meteorites for Ahmad Sitta in Sudan, it was a polymeteorite. We have meteorites from Motopipan, it was an HED. We had meteorites from fall in Normandy in France, it was an L609 gondrite, L meaning low iron. And then we had a fall in Tibet, it was an albright. It was in Germany. And there is, most recently, there's a fall in Siberia, which still has to be found. So these are sort of sample returns. So most of the data, however, we get
from this type of observations. You have a video security camera on one spot, video security camera on the other spot. You see the fireball go through the atmosphere. You track its path, and you measure with what sort of speed it's coming in and how it's slowing down. And we do that for in dedicated networks. We do it with video security cameras, with people's accidental dash cams and whatnot. And these are all the dedicated camera networks in the world. There's a lot of effort being done in Europe, some effort in the US, in Australia, Southern Australia. But otherwise, very little of the world is covered in dedicated camera networks, maybe 1% or so. So at any other place in the world, if there's a meteorite fall, then we are sort of forced to use whatever video is there. And 5 meteorites for which we have an approach orbit. And you would think 75 is a decent number, given just the effort it takes to do one. 75 is a decent number, but still the numbers are small because these are all the different networks that are contributors cameras. But if you look at the tally in terms of meteorite types, so that's here on the right. So you see 8, these are the ordinary gondrites. There is high iron, low iron, and extra low iron, very low iron, LL. The L/LL group belongs to LL. So this is part of the same, but sometimes put separate. Sometimes we have a mix in case of Benesov. These are the HEDs, Howardites, Eucrites, Diogenites. These are other anomalous, meteorite types, orbrites, enstetites, chondrites, uralites, iron, and these are the combinations chondrites. So in 2024, last year, when I wrote this review article, we had 28 H chondrites, we had 20 L chondrites, and we had 11 LL chondrites. We also had 4 HEDs and 4 combinations chondrites. So not big numbers, but that's what we have. And so the rest of my talk is basically about those different types and what their orbits so far tell us about where our meteorites are coming from. This is that Yarkovsky effect, where if the rock spins one way, it drifts that way. It spins the other way, it drifts that way. And you can see that very clearly, that the smaller the rock is, the more it has drifted.
And you can also see there was a massive collision event from this asteroid sitting down here, Massalia, asteroid 20 Massalia.
There was a big collision event, created a big massive crater on this asteroid. All that debris started moving this way, so all of this stuff is moving that way. All that stuff was moving that way. And there are more recent collisions that sort of fill in the space in between now. And so we think that there was about 40 million years ago, there was another collision on Massalia that creates that. But this, yeah. I'll show you later. It's about, I believe it was about 190 kilometers or something. Yeah. So this was, we're basically talking protoplanets here. This was just one protoplanet. This was one of these asteroids that really, you know, form big, but has since been eaten away at and gradually eroded. Yeah. Now this pattern allows us to determine what the age of the family is. So we can basically say, okay, this collision happened about 150 million years ago, while the stuff here in the center is more recent. So people were estimating about 40 million years ago. And so that's the task at hand is to compare this cosmic exposure age with this, the dynamical age of the asteroid family. That's a game to play. Okay, so where are we with our data? This is the case for the HEDs. So these are the meteorites coming from Vesta. We know they're coming from Vesta because you know, there is just this one big debris field out there. And so this is a good test to see if it works. So the HEDs are sitting here. This is the HED debris field. This is now semi-major axis of the orbit as we see it come in at Earth, and this is inclination. And each blue point is one asteroid fall. Now these don't have orbits. Unfortunately, we only have, you know, a handful of orbits, but we have a lot more HEDs for which cosmic exposure ages have been measured. And as you can see, there's a whole bunch of collisions. There's this one sitting here, that's about 22 million years. That's the main collision event in this group. But then there's a whole bunch of others. So some younger ones here, about 5 million years, around 10, and so on. So basically, every peak in this diagram is a collision somewhere. And all those collisions then result in this sort of a diagram. And you can see that in this case, these orbits correspond nicely with the evolution that you would expect from stuff coming from Vesta. Vesta sits at 7 degrees. The Vesta family sits at 7 degrees. And around that inclination is where we are seeing our meteorites. And Queba, the one here in South Africa, fits the bill. So we can actually see that, yeah, it's consistent with it having come from Vesta. There's one case here with a high inclination. That one had a close encounter with the Earth. That changed the inclination dramatically. And then you end up in that part of the diagram. The reason why these asteroids are so stand out so much is because they have really strong absorption bands. You can see a spectrum there in the corner. That's how these asteroids, that's the spectral shape of the asteroid, yeah. Good question. I forgot. I don't know for sure. It could actually be the one with the high inclination one, yeah. So the direction which is coming to the Earth is not, that depends on your observing geometry, where on the Earth you are and so on. So we're really talking about the orbit here. So in what orbit was it moving before it hit the planet? And then in what direction you're actually coming in depends on the velocity of the Earth, the velocity you have when you come in as an asteroid, and the sum of that. And then where you are on the planet, yeah. This one is very interesting with the 2 brackets, because that's Bunbury Rockhole, and Bunbury Rockhole has anomalous isotopes. So it's not supposed to come from Vesta, but it has a 22 million year cosmic exposure age. So it does look like it's your garden variety HED. Yeah. So anyhow, this is sort of the test to say, okay, fine, this works. By the way, I'll come back to this later. With these meteorites, we think that they're coming from Vesta itself, not from the family. We'll talk about that later. So these are now the ordinary chondrites, the low iron ordinary chondrites. And so we have a good number. You see the bunch of them are sort of around the inclination of 3-4 degrees. That's the cosmic ray exposure age diagram. You see there's a few collision events, but they're not as well defined because we don't have that many data. In the inner part of the asteroid belt is a family called Flora that has long been suspected as the source of these. And as you can see, it's consistent with the source of these LL chondrites. And the big asteroid Chelyabinsk in Russia was that type. So we think that Chelyabinsk also came from the inner part of the asteroid belt from this Flora family. So we think that Flora is indeed causing our LL meteorites. Now you can play this same game with near-Earth asteroids, with kilometer-size near-Earth asteroids. You can see this thing pass by the Earth. You can take a spectrum of them, but then you have to figure out whether it's an H, an L, or an LL, and you don't have a meteorite in hand to do that. So that turns out to be tricky. But people have done so, and they come up with a diagram that looks like this. So this is C major axis. Here's Mars, here's the Earth, and this inclination. And these are all the S-class asteroids, so asteroids with a rocky sort of spectrum that seem to be LL-like. And you see most of them seem to indeed come from the inner part of the asteroid belt where the Flora family is, about the same inclination as we see our meteorites coming from. So in this case, we can say that our meteorites and our 1 kilometer size near asteroid are basically coming to us via the same sort of mechanism. They all move towards the resonance. Flora sits right up at the resonance, so all these big asteroids can be delivered through that resonance, and then they evolve to come to Earth's orbit. Now that's LL type ordinary chondrites. If you go to H type, the high iron type ordinary chondrites, the story is completely different, and it's really cool. That's the green points. So most of our H-like ordinary chondrites seem to come from here's a 3-to-1 resonance and pretty high inclination. This is about 15 degrees, where the Maria family is. Up here is the Phukeia family. So they seem to come from a region high in the main asteroid. This is the inner asteroid belt. This is the central asteroid belt here. They seem to come from this high central main belt, high inclined area. Asteroids move in, end up in this 3-to-1 resonance, and that way make it to the Earth. That's for the 1 kilometer size things. Now let's look at our meteorites. This is our meteorite plot. Here is the new 6. This is the 3-to-1 resonance. This is that 1 resonance over. This is the central main belt. All these blue points and these white points here come from a low inclined source and an area just outside of this resonance. This, by the way, is the histogram of the H ordinary chondrites. You see there's a big peak at 7 million years, and there's a bunch of other peaks. But let's focus on these blue ones. So the blue ones, if you look plotted a little bit differently, so now I'm showing the perihelion distance, as that's basically how close they get to the sun, versus C major axis. They are very different between H and Ls. The Ls don't show that. There's this whole cluster of blue ones and so on are completely missing with the Ls. And you can see that the dispersion of the spreading of the H's is increasing if you go away from the 5-to-2 resonance. You have more and more cases where your perihelion distance is lower. So when they arrive at the Earth, the perihelion distance is 1. It's the Earth's distance. And then when they get perturbed in close encounters, then the perihelion distance becomes smaller, seeing major axis becomes smaller, and you get more and more dispersion like that. So, so this tells you that the source sits right outside the 522 resonance. And there is a source region there called Coronis. It's sort of an isolated S-class asteroid family that sits right here. And so, and you can see inclination distribution fits very nicely with the Coronis family. So we now know that Coronis is H chondrites. We also know that if your meteorite came in on an orbit like this, then you are sampling asteroids from that Coronis family, from that specific protoplanet. There was an asteroid called Coronis, got badly hit a long time ago, but within Coronis there are more recent collision events. And from the cosmic ray exposure rate distribution, you can see that we get meteorites from the last, in this case, about 80 million years. After that, you know, the inner part of all these eccentric orbits and the inner part of the solar system get cleaned out. So it's really the collisions in the last 100 million years that matter. Turns out, if you take these meteorites, all the blue ones, and these white ones here, if you take those and you look at the cosmic ray exposure ages, then this is the picture. We get 3 meteorites, Cossiccia, Morelli, and Apoquielpo, that have a cosmic ray exposure age of between 6 and 7 million years. We have 3 meteorites, sorry, we have 2 meteorites that have cosmic ray exposure ages, one for 11.8, one 14 million years. And then there's one case of an 83 million year cosmic ray exposure age. Turns out that in Coronis are three collision events in the last 100 million years called Karen, Coronis 2, and Coronis 3. Karen is said to be 5.8 million years. So that would correspond to that first group. Coronis 2 was said to be between 10 and 15 million years. That would be nicely corresponding with the second group. And Coronis 3 would be less than 100 million years, which would be nicely corresponding with this 83 plus or minus 11. So I'm saying we are seeing meteorites come from all 3 collisions in the Coronis family. So if you determine the cosmic ray exposure age of an H chondrite that came in on this sort of orbit, you not just get a meteorite from Coronis, you get a meteorite from one of these 3 debris fields. So you could sample, you know, the properties of those debris fields. It's a literally sample return without, you know, you taking the effort to go there, pick up a rock, and bring it back. So that's the picture. It's not. It may be a lot more complicated. There's a lot of debate going on in our community. In particular, there was a nice paper by Brosedol that said, no, wait a second. We think that Coronis 2 is 7.6 million years, and it has a very steep size distribution. There's a lot of small debris created. So we think that all these are coming from Coronis 2. I don't know. I think that I see meteorites come from all 3 debris fields, because otherwise I don't know where my other meteorites are coming from. Okay, so those are the blue ones. What about the other H chondrites? So there's 2 groups. One, there's a whole bunch of H chondrites being observed with very high inclinations. And what is peculiar about those is that they have also the short cosmic ray exposure age of 6 million years. These round circles, open circles, those are the 6 million year cosmic ray exposure age, which suggests to me that that is not from Coronis. To go from there into orbits like that, you would expect the whole evolution to see and see those. I think there's another source of these 6 million year H chondrites, and that's in the top of the central main belt in this area, where also our really big kilometer-sized asteroids are coming from. And there is a second source as well, 18 million years. And I think that these are our asteroids, with the short ones and the 18 ones. And the most likely candidate for the 6 million year cosmic exposure age is this family here, Giannini. This is about 6 million years old, dynamically. The 18 one, I'm not so sure about. I suspect it's coming from Maria up here, but we don't have, people haven't determined dynamical ages yet. So there is at least two more sources up there in central main belt. And then there is this group that sits, so those are the meteorites up here at the high inclination. See, they're completely missing with the L's. With the LLs, we see there's one, Benesov. Benesov is, I think, represents another source of LL chondrites. So it's not just flora. Benesov also comes, I think, out of the central main belt, where there is a family called Eunomia. And Eunomia has LL spectra, and nearby is a lot of H chondrites. And sure enough, Benesov was a mix. It was both LL and H's. Yeah. But there is also a debris field of H chondrites here in the inner main belt, this group. And that group is a puzzle. So it's basically, it's this one here, the red one. Those have a cosmic ray exposure age of 35 million years. So there is a source of about 35 million years of collision in the inner main belt. And I think that source is in the Massalia family. And that's sort of shown here. So this is the inner main belt. The Nu6 is on the inside, 3-to-1 resonance on the outside. There are two big families there, one called Massalia, the other is called Herta. And the Massalia family, I think, is H. But other people are claiming that it's L. I need it to be H because if I want to have a source of H chondrites anywhere in the inner main belt, that's the only candidate. And Macetadol did identify this 40 million year cluster in Massalia, which fits just nicely with my cosmic exposure ages. So I'm saying, you know, this looks like that this is a very likely source of those. And I checked and see if the inner main belt H chondrites were different than the outer main belt H chondrites. And there are subtle differences. But this is definitely something that, you know, in the future can be discussed. So that basically means that if you have a meteorite fall, an H chondrite, or you need to know the orbit. You want to be able to tell what's inner main belt or outer main belt. Also to sort of confirm this picture that the 35 million year H chondrites correspond to that. So this is the debate we are having. So Macetadol wrote a very nice paper in Nature about this Massalia family. And so his claim was that this was the source of the L chondrites, not the H, but the L's. And the way he arrived at that was to carefully compare the position of bands and the ratio of band intensities for these three meteorite types to what he was measuring from the families. And so you see at the top there is H, the blue is L, the orange is LL. That data is for meteorites. And then all the orange dot is for each individual family. So this is Eunomias here and Floras here. So those are clearly LL. They're sitting all the way here. Coronis we now know is H, so it sits here. And Massalia is this one, the one sitting right below it. And he basically said that Massalia was plotting more in the LL, in the L regime, in the blue band, instead of in the gray band. But if I look at this data, I'm noticing that Flora and Eunomia are plotting off the chart. They're really much further down there. So the way I sort of interpret this is that it probably is more like this. In which case Herta would plot in between Flora and Massalia. And Herta would be the one, the L asteroid source. And Herta is the family that sits just above it. So that is this one. That's this family. And it's a really hard to study family because there's another debris field sitting right on top of it called Polana. So you have to do spectroscopy. You have to make a distinction which is which. So we don't have as much information about this case. So these are the L's, all the L. And the one thing immediately that you see if you look at this is that L's are coming from the inner asteroid belt. There's no L's coming from the outer or central asteroid belt. There's supposed to be a big family called Gephion sitting here. So you could convince yourself saying that maybe this one is coming from Gephion, but who knows? Gephion could also be H. Everything seems to come from the inner asteroid belt. And this is the new 6 resonance here. This is the 3 to 1. We think that this debris field here is Herta, is what producing it. And so the meteorites could come this way, it could come that way. This one is much more efficient because you're not getting as close to Jupiter on the far end. But some of them are coming through the new 3 to 1 resonance as well. But most of it is really just from that one source. And I think that that's what the Herta family is. Now, if you look at the L-class, L-like, S-class asteroids, they all come out of the 3 to 1 resonance at about 5 degrees. And so they sort of come from here. This is where they're clustering. And I think that's because the L-class is against, you see, they sit up against the resonance on this side, but are further away on this side. So the big asteroids, you know, take some time to move to the resonances, and then give you this sort of preference for one resonance or the other. Yeah. So I'm thinking that all the L's are related to Herta, and the L's have this really interesting sort of history in that there was a massive collision event 468 million years ago that showered the Earth with so many meteorites that you can find them back in the geologic record. You can literally dig a hole in the ground and you can find an Algondrite meteorite. And at that time, it must have been absolutely crazy. So for a period of multi-million years, the influx was dominated by Algondrites. This is a Koi in Sweden, where they found that. And it turns out that our meteorites have this 470 million year collision event signature in the rock. If you measure argon ages for Algondrites that are shock blackened, that really had experienced this collision, then you find that 470 million years ago, the argon was reset. So you lost all the argon from the meteorite. And so this collision in the asteroid belt had to have been very violent. And yeah, sure.
One of these Swedish Ordovician meteorites actually an Earth creature, an Ammonite or something.
Well, yeah, I think that's this graph. That's probably the Ammonite, but I don't think it killed it. Or at least you can show it killed it. It got deposited with the object, with the creature at the same time. Yeah. So this is these are our candidates. So Massalia is down here. So here is the size. Sorry, it's 145 kilometers for Massalia. And Herta is only 79 kilometers. But these are still, you know, pretty protoplanetary sort of sizes. These are the big asteroids. Now, the strange thing with Herta is that Herta has a debris field of Algondrites, S-class on Algondrites, but Herta itself is dark. And so while Massalia looks like the meteorites it's spread around, Herta doesn't. And but if you look at Herta, what it does look like is what we call shock blackened Algondrites. This is a shock blackened Algondrites. It's so heavily shocked that they mobilize all the iron and you make your meteorite dark. And it does not hold on to its fusion crust. I initially didn't recognize this thing as a meteorite because there is no fusion crust. There's a little bit there. You see where it's white? That's where they're able to hold on to its fusion crust. But otherwise it didn't. So I think that Herta is covered in this stuff. So the meteorites that are not shock black and they just look white or light colored, like the one over there, the inside. Yeah. So and this was one found in California. It does have that 470 million year argon age signature. Yeah. So that's what I think That's where I think all our algondrites are coming from, and but which was the source of this massive rain of algondrites when the family formed 476, what is it, 468 million years ago. Yeah. Okay, deep breath. Are you guys following all this? Or okay, good. So the next group of meteorites I want to talk about is carbonaceous chondrites. So those are the blue ones, the primitive ones. And the story there is more complicated. Less well known. So the one case we understand now is Polana and Eulelia, because Polana and Eulelia is this thing that sits right on top of Herta, that family. That family is the source of Bennu and of Ryugu. And so the samples that were brought back in the OSIRIS-REx mission and the Hayabusa 2 mission, those we now know are CI types. And so we know that these families are CI. Yeah. The CMs, however, don't seem to come from the family that's right above that, which I had expected. They are, so the CMs we've seen so far all come out of the 3-to-1 resonance, a very low inclination, less than 3 degrees. And so that means that the source is somewhere in the outer asteroid belt or in the pristine main belt. And there is a couple of candidates. One is this Themis family, big debris field, but not all Themis asteroids look like CMs. So this is still a big question. But that's where we see our CMs. Now with the CMs, there's something interesting going on, and that is that all our cosmic ray exposure ages are really young. That means that once these rocks get into these eccentric orbits and they sit in near space, they don't last. They will fall apart on you. And they will continue to fall apart. And so there's like this ongoing cascade. Now, these 4 that we have so far were all different. So they all come from different original asteroids. But yeah, that's what's going on with CMs. And it's probably also what's going on with CIs, which just don't have any orbits. So Themis has this Beagle family. It's less than 100 million years. That's a good source, potential source. It has sort of the right spectrum. And it could deliver CM-like asteroids in the near space, and then over time it could produce some of our meteorites there. Other sources, Polana is CI, so that's not. Sulamite is a bit too high inclination. And there is one other potential source that's up there is Veritas, also has CM-like spectra, but Veritas also too high inclination for it to be consistent with what we're seeing. There's one meteorite called Flensburg, and Flensburg is a C1 ungrouped, but it has CM affinity. That one may be coming to us from Vesta. It came right out of the 5-to-2 resonance, from Veritas. Yeah. So these could be related. We may have a sample. And that leaves us with this group, the weird EOS family from carbonaceous chondrites that are sort of in the CO, CV, CK type. Both 3 are related. Meteorite types are related. They have very little carbon in them. They almost look like ordinary chondrites, but they have really, they're rare to fall. So until recently, we had no falls to verify this. But I would expect if they would come to us, they should come to us out of the outer asteroid belt, the 5-to-2 resonance. So sort of from this resonance here. And then sort of from this inclination, which is about around 10 degrees or maybe a little bit higher. That's what my expectation was. And so when we had a meteorite fall in Tucson last year, and that came out with a C major axis of 2.74 AU and an inclination of 14 degrees, I told the meteorite hunters, I would think that this could be a CO, CV, or CK type meteorite. That's what I was expected and hoping to find. And people went looking initially and couldn't find anything, and then later they went back, and then sure enough, a CK carbonaceous chondrite was found. And this is only the 3rd CK fall that we know of that was recovered. So there's Karuna, and then there's Kobe in Japan, and this is now the 3rd one. So this is amazing. So this works. You can look at your orbit, and you can make inferences about what meteorite type you expect to find on the ground. And it's maybe visual thinking, because there's other sources as well that can give you orbits that high, I immediately admit. But I thought this was just a fantastic result. So this is the very first time that a meteor type was predicted based on the orbit we measured. So yeah, so that's where we are with our sort of assignments on the different meteorite types. So I have a few more slides on Motopi-Pan and so on if people are interested in it, but you guys have listened long enough. Hope this is interesting. Thank you.
Thank you, Peter. The students have left because they've got lectures.
No
apologies for the frequency of people moving out. We'll have some questions. We'll ask them via the microscope. The microphone.
Where do irons and pallasites come from? I'm not finished. Oh, yes.
I don't know.
So the trick with irons is very interesting because irons have very high thermal conductivity. So this whole business with Yarkovsky drifting the meteorites to the resonances doesn't work. These meteorites stay up there forever. And so the cosmic exposure ranges that people have measured for irons go up to 1.5 billion years. So that's why irons is a different story. Yeah. 1.5 billion. Yeah. And that's just because Yarkovsky is, people think that the reason why that is because Yarkovsky is so ineffective.
Could I just change that and say, are there any ions that have low ages? Or are they all much older than the silicate meteorites?
That I don't know. So we have one iron for which we have an orbit, and that one iron came out of the inner asteroid belt. Yeah, but that's not enough for us to pinpoint.
Okay. If each type of meteorite comes from a different place in the asteroid belt, a different parent body or a different family or a debris field, as you call it, then that has to say something important about how the asteroid belt itself has formed. So, for example, when I was a young boy, I was taught that the asteroid belt is not to be thought of as a broken up planet into billions of pieces, but instead the asteroids formed by themselves in some other form of way. But how can you comment on that? It seems almost like the ones that you might consider deep, like the irons coming from the inner asteroid belt, the ones that are shallow, like the carbonaceous content from the outer. So that could be depth within a parent planet.
So the way I think about it is not that what you're seeing is differentiation in one big planet that fell apart, but rather that the asteroid belt was populated by protoplanets, by objects that grew to 100, 200 kilometers, and a bunch of them filled that space that was left empty after Jupiter came in and went back out. And a whole bunch of stuff came from the inner part of the solar system, the inner part of protoplanetary nebula. Another chunk came from the outer parts of the protoplanetary nebula. And those objects, those 100 kilometer, 200 kilometer size objects, up to Ceres, they are still with us in a way, some of them, as the large asteroids we're seeing. And so the Coronis is a large asteroid, is its own debris field. That's a different parent body, if you like, a different protoplanet, had its own evolution, its own history, its own formation, compared to if there was indeed an H chondrite debris field in the inner asteroid belt, or the one sitting there up there high in the central main belt. That object had its own history, its own evolution. And so they all sample different evolutionary processes in different locations in the protoplanetary nebula. No.
I've got a whole bunch of questions. This Jacob, how did you say it? I want to say Joukowsky dispersion. Can we not calculate back and get an age from that also?
Yes,
I mean-
but that's exactly what we're doing.
Seem to agree with the cosmic exposure age.
Yes.
Okay.
Now, that's important. So, yeah. That's a key thing. So what we call that the dynamical age, that the age you derive from Yarkovsky, that's the dynamical age. That age corresponding with the cosmic ray exposure ages I'm seeing with my meteorites means that the meteorites are not continuing to fall apart and break apart and erode and have lots of collisions and go into smaller pieces. It basically means that the meteorite that we are seeing was formed when that debris field was formed. And that debris field that we're seeing in these asteroid surveys, all these little clusters, you know, those are kilometer-sized asteroids. So those are big collisions, big collision events. And they created a massive amount of small pieces. And those are now our meteorites. That's sort of the new way to look at it.
Okay. And do we see one of those from the collision with Mars? Do we see a debris field from the
Yeah.
because we have Martian meteorites.
Yes. So with the Martian meteorites, it's the same thing. You had a collision. In this case, it was a cratering collision on Mars itself that threw a bunch of material into space. Those things went into near Earth orbits and have been waiting since to hit us. And they do occasionally. Yeah.
So you showed the HED for the HED meteorite class, the ones related to Vesta. You showed that one meteorite had a different composition from the HED, but had the same age of 22 million years.
Yeah.
Could that meteorite be representing the impactor rather than the target, Vesta?
Yeah, that would so the different cosmic signatures, if they are real, really means that the parent body was different. So that means that somewhere there is another HED asteroid from which a piece came that then collided with Vesta. Yeah. So you can't you can assign it to a target, to a projectile, but you still have to worry where that projectile came from. And so fundamentally, if it's other cosmic, other oxygen isotope composition, then it should mean that it's another source, another parent body.
Okay, well, Peter, thanks very much. It's nice to see the context in which us scraping around on the ground, finding the asteroids can be put in terms of the bigger solar system. And we look forward to the continuing work because we are working with you on several things. And now we know that we must chase these things when we see that bright light in the sky, because you might have some things to say about it, and we can start checking this as we go forward. So safe travels, and thanks for visiting.
Pleasure.